Hi, during this lesson, we're going to work on using the solubility rules to predict whether or not an ionic compound is soluble or insoluble in water. If you will, please go to Canvas and pull up a copy of the solubility rules, as I'm going to refer to those a lot during this lesson. And perhaps having a periodic table and your ion chart is going to be something that you also find quite handy. After we learn how to use the solubility rules to predict the solubility of the compound, we're going to work on writing equations for double replacement and applying the solubility rules to figure out which one of those compounds that is formed is actually the precipitate. Okay, so a little bit of vocabulary that's going to make it helpful. The word soluble, that just means that it's going to dissolve in water. And what we do usually is mark that substance with an AQ subscript after the formula to indicate that it is aqueous or dissolved in water. Now, when an ionic substance dissolves in water, it breaks apart into the ions. We're going to work on that a little bit during this presentation as well, because it's important for us to know what ions and in what ratio they are formed when the ionic substance breaks apart after dissolving. Now, the word insoluble means that the substance will not dissolve in water. And these substances you're going to see marked with an S as the subscript for the phase notation, meaning that it is a solid because it will not dissolve in the water and make a solution. Now, I'd like you to get your solubility rules handy, and I want to show you how to use those by going through these three examples. So let's take a look at the first example, the AgNO3. Now, most of these rules are written based on what's the anion in the compound. Remember that the anion is always the second one, and this is where your ion chart will come in handy. If you don't remember exactly what NO3 is, you can find it in the ion chart for the polyatomic ions. NO3 minus 1 is nitrate. So then you look at the solubility rules, and you see that the rule for nitrates is the first rule. And it says all nitrates are soluble. So that means that all nitrates, no matter what the cation is, are going to be soluble. And so this compound you would see marked with something like an AQ subscript if phases are being noted in a chemical reaction. Take a look at the next one. OH is hydroxide. Rule number 6 says that the hydroxides are insoluble, and then it lists a couple of exceptions. So let's take a look at the exceptions. So some of the exceptions are the alkali metals. Okay, the alkali metals are the first column on your periodic table, not the hydrogen, but the other ones like lithium, sodium, potassium, rubidium, cesium, and francium. So iron's not one of those. Ammonium, that's on your ion chart. It's a polyatomic cation, NH4 plus 1. And then they list a couple of others like calcium, strontium, and barium. So iron is not one of the exceptions. So it goes by the regular rule that hydroxides are insoluble. And that means that we're going to mark it with an S to indicate that it would make a solid. If it was placed into water, it would not dissolve. It would be a solid and sink to the bottom of the beaker. Now, the last one, you just see an S right here. Remember that if it's a single element, that the nonmetals make anions. And the nonmetals that make anions, when they form an anion, the charge is determined by which column it's in. Sulfur is in the same column as oxygen, and we assigned a -2 to that column because they need 2 more electrons to fill their valence shell. And remember that the way that we name those ions is that they end in an IDE. So this would be, somehow I got my laser pointer there instead. This would be called sulfide, okay? And that's an important distinction because there's sulfates on the solubility rules, and then rule number 7 is about the sulfides, and this is a sulfide. So in rule number 7, all the sulfides are insoluble, and then they list some exceptions. So there's the alkali metals, then it says the alkaline earth metals. Now that's the second column. And the second column, let's see, calcium is one of the elements in the second column. And so that's one of the exceptions to the rule. So instead of being insoluble, it's going to be an exception to the rule and be the reverse of the rule. It's going to be soluble, and we would mark it with an AQ. So that's how you read the rules. You just find the rule that applies to this compound and read it, and then see if the cation is one of the exceptions or not. Now, when you're looking at the rules, the first 3 tell you what's soluble and then give you some exceptions. Rule 4 is talking about some cations. Anything with a cation that's an alkali metal or ammonium is going to be soluble. Rule 5 is talking about acids, which start with hydrogen, and those are soluble. The common acids are, at least. Things like hydrochloric, sulfuric. And then rules 6, 7, and 8 tell you what's insoluble and give you some exceptions. So give it a try. Here's a list of compounds that I'd like you to try. What you can do is pause this recording, use your solubility rules to make your predictions, and then restart this recording to see how you did. Okay, welcome back. Hopefully you have practiced these. Rule number 1, the nitrates are always soluble. For number 2, we're going to look at rule 8, which is about phosphates. They're insoluble except for alkali and ammonium. Well, iron is not one of those, so it's going to be insoluble. Number 3, this is an oxide. So we look at rule number 6. All oxides are insoluble, and then they list a lot of exceptions, and the SRO, strontium oxide, is on the exception list. So it's going to be the reverse of the regular rule, and it's going to be soluble. Cl is chloride. That's rule number 2. The chlorides are soluble. There are some exceptions listed. Cobalt's not one of them. So it's soluble. And then for number 5, we want to look at the sulfate rule, which says that they're all soluble except for 5 exceptions. Potassium is not one of them, so it's going to be soluble. So when you did your predicting, if you got 1 solid and 4 aqueous compounds, you were right on the money. Now, if you got only 3 or 4 of them right, you might want to practice a little bit. And if you got less than that right, you definitely want to give it some good practice. I shared a link to a Quizlet with you. I think I have 20 different compounds listed on the Quizlet. And on the front of the card is a compound. You can use the rules, determine whether or not you think it's soluble or not, and then flip the card over and see if your prediction is correct. So definitely take some time to practice those Quizlet cards. I shared that link with you in Canvas. So what are some other things that we need to learn through this lesson? Well, remember that if something is soluble and it dissolves in water, that means it also breaks apart into ions. So for example, if I have sodium chloride, which is table salt, and it dissolves in water, it's not going to stay intact in its crystal lattice. What's going to happen is the crystal lattice will break apart to form cations and anions. So you list the cations first and then the anions. You list the charge on the ions, and you note that they're each dissolved in water. Now, if you have something that has some subscripts, like for example, calcium chloride, that is also soluble. You've got to use the subscripts to help you figure out the charges, like calcium is +2. But also, I tend to see this a good bit from some of my students. They'll do something like this, and we know that that is not the formula for chloride. Chloride is just Cl-1. Cl2 is when you have molecular chlorine, okay? And that's when it's by itself and it's neutral. It's not neutral here, it's an ion. So it's going to be written as Cl-1. A lot of people then are concerned, well, what about the 2? Well, that's where you balance it out by indicating that when a unit of calcium chloride breaks apart, you're going to get 1 calcium and 2 chlorides. So you kind of balance it out using coefficients and write a dissolving equation to show that it's going to make 2 of those chloride ions. Here's a few for you to try. Again, maybe the best thing to do would be to pause the presentation, try them. Now, all of these are soluble, so you don't have to worry about checking the rules, but you can just for practice. And then what I want you to do when you have these formulas written down is practice breaking them apart into ions. Once you've had a chance to do that and you're done, restart the presentation and check your work. All of these are aqueous. And so what we want to do here is break them apart into the ions that form them. So in the first one, it's going to break apart into silver ions and nitrate ions. I think this is good practice because occasionally I will have students who will break the nitrate ion apart into some nitrogen and some oxygen. And that doesn't happen. It actually stays intact as a group. Remember, there's covalent bonds holding the nitrogen and oxygen together within the polyatomic ion. And the group, NO3, just has an extra electron, so that makes it an anion. So it will stay together. Only the ionic bonds, pull apart out of the crystal lattice and float around in the solution. Those covalent bonds within the NO3 group, those stay intact. You have to write it together. So let's try a few others. In the next one, we're going to get calcium ions. And we're going to get 2 hydroxide ions. Hydroxide ions also, that's a group. Keep it together. In the next one, we're going to get 2 ammonium ions and 1 sulfide ion. For number 4, we're going to get a cobalt ion. Now, you might be wondering, well, which cobalt do I use? Cobalt's on my periodic table, not my periodic table, my ion chart twice. And that's where you go back and you look at the formula. You can see here that the cobalt has a charge of +3 because of the formula COCl3. And then you have to remember to show that you get 3 chlorides when it breaks apart. For the last one, we're going to get 2 potassiums and 1 sulfate ion. Notice how I included the charge on all the ions and then also indicating that they are aqueous. Okay, so let's move on to our last goal, that being able to write then the double replacement reactions. So when it's a double replacement reaction, remember that they swap the ion partners. It's 2 ionic compounds, and they swap partners to make 2 new ionic compounds. One of the things that I suggest to my students is just write the formulas of all the ions so that you know what you're working with. So these are the 4 ions. Now, when they do their swapping, remember that the positive ion from one compound goes with the negative ion from the next compound. So when you name them and write the formula, you always put the positive ion first. So I'm going to put the lead 2 And then I will put the hydroxide portion of the name. Now the other compound that is formed is going to be the positive ion from the second compound with the negative ion from the first. I meant to circle that whole NaNO3. I missed just a little bit, so let me redo that. So you got to use the whole thing. So you always in the name put the positive ion first. So I'm going to list the sodium first, and then I'm going to list the nitrate. Now I can write formulas for everything. For the lead nitrate, lead is +2 and nitrate's -1, so I need 2 of my nitrates. Sodium and hydroxide are +1 and -1, so I just need 1 of each. After the arrow, I have lead hydroxide. Lead's +2, hydroxide's -1. And then I have sodium nitrate +1 and -1. So I just need 1 of each. Notice that the only time that you use parentheses for the polyatomic ions is when you're going to put a subscript outside of the parentheses. For the sodium hydroxide, I don't need a subscript, so no parentheses. For the sodium nitrate, I only need 1 nitrate, so no parentheses. Other things that you need to do, you need to balance it. Every chemical equation always needs to be balanced. And then you need to indicate the phase notations so that you can tell which one is the precipitate. So nitrates are always soluble. So I can just go ahead right away and indicate, yep, they're all soluble. And now I want to look at rule number 6. It says that the hydroxides are insoluble, and it does list some exceptions, and alkali is one of those exceptions. Sodium is an alkali metal, so it's an exception. But lead is not one of the exceptions, and it is going to be insoluble. So now I have a balanced chemical equation with phase notations. The precipitate is going to be the lead hydroxide. A precipitate is a solid that is formed as a result of a reaction in solution. Since these two reactants are both solutions, they're dissolved in water, and when they come together, a solid is formed. That solid is now known as a precipitate. The other product that's aqueous, the sodium nitrate, those ions would remain dissolved in the water, and if we set up a piece of filter paper and conducted a filtration, the lead 2 hydroxide would be caught in the filter paper, and the sodium nitrate would pass through with the water. Okay, I have one more of these. And the reason I have this one is because anytime it involves an acid, students find that a little bit tough. A lot of times I'll get students, they want to say zinc acid and chromic chloride. Well, that doesn't make any sense. So again, I say, I think the easiest thing you can do is figure out what are your 4 ions. When it's an acid, remember your cation is always H+1. For your anion, you have to look at your acid naming rules. Remember that if it's chromic acid, that means it's chromate for the anion. Remember, the white house gate is thick. If the anion ends in ite, then the acid ends in OUS. But if the anion ends in ate, then the acid ends in IC. So this is the chromate anion, and I look it up on my ion chart, and I find that it is CrO4-2. So now I'm ready to put things together. So I can see the zinc is going to go with the chromate. So that's one of my products is zinc chromate. And my other product is going to be the H with the Cl. So to name it, I have to know my other naming rule. When it's chloride, if the anion ends in ide, then the acid name, remember, has to begin with hydro. So this is hydro, then you go with the base of the anion, chlor for chloride, but the I gets changed to ic. and that is hydrochloric acid. Now I'm ready to write all of my formulas. I have zinc chloride. I have chromic acid. I need 2 H's for this one since the CrO4 is -2. Zinc chromate, +2 and -2, that's just going to be 1 of each ion. And hydrochloric acid, +1, -1, so I just need 1 of each ion in hydrochloric acid. I'm going to have to balance this by putting a 2 here. Then I can start checking the rules. Rule number 2, chlorides are soluble. Zinc is not an exception. Rule number 5, all of the common acids are soluble. And then rule number 8. It says the chromates are insoluble. There are some exceptions, alkali metals and ammonium, but zinc is not one of those. So the zinc is now identified as our precipitate. Now, what if you put 2 ionic compounds together and no precipitate is formed? In that case, you don't write a balanced reaction for it because there really is no reaction. If you put 2 solutions together that have ions just kind of freely moving about water, and you put them in the same container, and now all 4 of the ions are just freely moving around the water because none of them have precipitated to form a solid, then all you've done is just create a mixture of 2 solutions. And a mixture is not a chemical reaction. So you have to get a precipitate for it to actually be a double replacement reaction. Now, hopefully, you've learned how to use the solubility rules. And again, you can practice that with the Quizlet. But I have also put in Quizlet a set of cards where you can practice predicting what are the compounds that are formed. And you can use the solubility rules to figure out which one of the 2 compounds is your precipitate. All of them that I put in that set of cards do have 1 insoluble compound. So there is a precipitate. There's none that are mixtures or no reaction. There's a third set of cards where you can just work on breaking compounds apart into the ions that form them. So that'll help you with writing dissolving equations. Remember to also, when you write a double replacement reaction, balance it and add the little AQs or S's, which are called phase notations, to complete it and indicate which product is the precipitate. So good luck. Practice with the Quizlet. After you're done practicing with the Quizlet, there is a Google form for you to answer. But I would practice first to make sure you're highly proficient, because the Google form, that's graded and it's worth 12 points. So good luck. And, let me know if you have any questions.